Hello there, and welcome to the Sleepless Scientist, a quiet place in the vastness of the cosmos where your thoughts can drift, and knowledge becomes a gentle companion for the night. Tonight's journey invites you to settle into something both humbling and wondrous, a slow, immersive unravelling of how we decode the universe. From the faint whisper of particles that flicker in empty space to the grand sweep of galaxies drifting apart across billions of light years, we'll wander through scales too large to hold in the mind and too small to see with the eye. And yet, somehow, all of it comes together in the delicate weave of reality that surrounds you right now. But before we begin, if you find calm in these quiet explorations, you're welcome to like the video and subscribe, only if it feels right. And when you're comfortable, I would love to know where in the world you're listening from tonight and what time it is for you in your corner of the sky. It's always a joy to see our little gathering of dreamers scattered across the globe, each settling into rest under a different patch of stars. For now, feel free to dim the lights, let your shoulders soften, and maybe turn on a small fan or a quiet background hum. Something steady that keeps you grounded as your thoughts begin to loosen. And if your mind drifts as we wander through these ideas, that's completely fine. Let it drift. The universe will still be here, unfolding softly around you. So when you're ready, let us ease into this calm beginning and gently step into session 1 of our journey through the mysteries of the cosmos. If you imagine yourself floating far from Earth, far beyond the pull of the sun, past the orbits of the giant planets, past even the frozen edges of the solar wind, there is a tiny machine still travelling, still humming faintly as it moves through the quiet dark. Voyager 1, launched in 1977, continues its slow journey outward. It has no destination, and yet its presence feels purposeful, like a messenger slipping into the unknown with a postcard from home tucked inside. Decades ago, when it was already billions of kilometres from Earth, Voyager 1 turned its camera back toward where it came from. What it captured was not a majestic blue globe or a swirl of continents and oceans. Instead, Earth appeared as a pale speck suspended in a shaft of scattered sunlight, a small, almost invisible dot floating in an immense sea of darkness. Carl Sagan described it as a mote of dust suspended in a sunbeam, and even now, looking at that tiny dot can make your thoughts fall silent for a moment. It's unsettling in its smallness, but soothing too, because wrapped inside that dot is every memory you've ever had. Every sunrise, every conversation, every quiet moment like this one. That single image became a turning point in how we think about the universe. It didn't tell us we were unimportant. Instead, it reminded us of how far our curiosity could carry us. A small speck can still send a machine into the void, still send questions into the silence, still listen for echoes from the beginning of time. Over the last 50 years, our understanding of the cosmos has changed in ways that earlier generations could scarcely have imagined. When Voyager launched, astronomers hadn't yet seen a single planet outside our solar system. They thought galaxies were numerous, but not unimaginably so. Black holes were theoretical beasts rather than everyday residents of galactic centres. The idea that the universe might be filled with invisible matter and driven by an even more mysterious form of energy was almost unthinkable. And yet, discovery after discovery slowly reshaped the map of our understanding. What seemed familiar became strange. What seemed simple became layered with complexity. Sometimes, the universe felt as if it were gently correcting us, saying, "Look again." One of the most quietly dramatic changes was the shift in scale. When scientists aimed the Hubble Space Telescope at what looked like an empty patch of sky, a region no larger than a grain of sand held at arm's length, They expected a handful of faint objects. Instead, the image revealed thousands of galaxies, each a swirling island of stars. Later, when wider and deeper observations were made, the number grew into the trillions. Suddenly, our Milky Way became only one among countless others, drifting in a universe that seemed to multiply every time we looked closer. Another shift came from listening to the cosmos rather than just looking at it. Space is silent in the sense that sound cannot travel, but the universe leaves behind other forms of memory. One of them is a faint glow that fills all of space, light left over from the moment the universe first became transparent, more than 13 billion years ago. Astronomers call it the cosmic microwave background, but you can think of it more softly as the universe's earliest photograph. It shows tiny ripples in temperature, subtle variations that later grew into galaxies, clusters, and the vast web-like structure that binds the cosmos. Those ripples told us the universe is old, almost 14 billion years old. They told us its overall shape is remarkably flat, like a calm lake stretching to the horizon. And they told us something even more surprising. Most of the universe is made of things we cannot see. The stars, planets, and glowing gas that fill our telescopes are only a small fraction of what truly exists. This realization did not arrive all at once. It seeped in slowly, through decades of measurements and questions that refused to go away. Every time researchers tried to describe how galaxies move or how clusters hold together, the numbers didn't add up, unless they included something invisible, something that didn't emit light, but shaped the motion of everything around it. It's a humbling feeling to realize that the familiar glow of the night sky is only the surface of a much deeper structure. Even now, as you listen to this, dark matter threads through the universe in vast filaments, creating a hidden scaffolding on which galaxies gently hang. We don't yet know what dark matter is, but we can feel the imprint it leaves on everything else. And through all of this, Voyager continues outward, carrying its quiet message, that even on a pale blue dot, life can wonder about the stars. That curiosity can push us far beyond our smallness, and that sometimes, stepping back to see the whole picture makes the universe feel both larger and more intimate than we ever expected. As we drift deeper into tonight's journey, we'll begin to explore the strange, invisible forces that shape the cosmos and the unexpected ways they challenge our idea of reality. If you step outside on a clear night and look up at the sky, it's easy to imagine that the stars you see are isolated lanterns in a quiet darkness, beautiful but simple. For most of human history, that was exactly how they appeared. A scattered handful of points, each one steady in its own small patch of sky. Even as telescopes grew larger and our maps of the heavens became more detailed, there was still a sense that the universe was essentially familiar, like a well-worn trail through the woods. But the last half-century has slowly replaced that old familiarity with something far more astonishing. In the 1970s, astronomers could only guess whether planets existed around other stars. Science fiction imagined alien worlds because none had ever been observed. When Voyager 1 launched in 1977, not a single planet outside our solar system had been confirmed. The Milky Way felt unique, almost like a private home in a quiet galaxy. But as the decades passed, our tools sharpened. Telescopes began detecting small dips in starlight, tiny rhythmic dimmings that signaled a planet passing in front of its star. Each dimming was like the soft blink of a cosmic lighthouse, a hint that something was orbiting far away. At first, discoveries came slowly. A planet here, another there, but then technology leaped forward. Dedicated space telescopes like Kepler began watching tens of thousands of stars at once. Night after night they recorded the faintest flickers, and the silence broke open into abundance. Thousands of worlds appeared in the data, hot giants swirling close to their suns, colder worlds drifting farther out, rocky planets not unlike our own. Some orbit 2 stars at once like scenes pulled straight from stories. Others circle ancient suns in quiet, stable paths. And the more we found, the more obvious the pattern became. Planets are not rare at all. They are everywhere. For every star you see when you look up, there may be several planets circling it, each carrying its own history and weather and long silent cycles of days and nights. And just as our sense of planets expanded, our understanding of galaxies underwent its own quiet revolution. For most of the 20th century, astronomers believed galaxies were numerous but still countable, perhaps a few billion. Even that seemed large enough to stretch belief. But in 1995, the Hubble Space Telescope did something quietly extraordinary. Scientists pointed it at a patch of sky that looked completely empty, a region so small it could have been covered by a grain of sand held at arm's length. They expected to find perhaps a few faint smudges. Instead, after days of gathering light, the darkness bloomed into thousands upon thousands of galaxies. Each dot was not a star, but a vast island of hundreds of billions of stars scattered across the deep. Later observations pushed the estimate even further. Our universe may contain not just billions or tens of billions, but trillions of galaxies. Trillions. If you tried to count them one by one, lingering just a second on each, you would run out of time long before your count reached even a tiny fraction of the total. And in those galaxies, stars form and age and collapse by the millions. It is a cosmic forest so dense that even imagining it begins to feel like dream work. Yet, perhaps the most surprising revelation came not from the number of galaxies, but from what sits at the centre of nearly all large ones. For decades, black holes were viewed more as mathematical curiosities than as real objects. They were the strange solutions that appeared in Einstein's equations, places where gravity became so strong that not even light could escape. But gradually, evidence began to accumulate. Stars near the centre of our own Milky Way were observed whipping around an unseen point, moving so quickly that only something incredibly massive could be responsible. Over the years, their orbits traced out an unmistakable story. At the heart of our galaxy lies a dark mass weighing about 4 million times more than the Sun, and the Milky Way is far from unique. As observations improved, astronomers learned that almost every large galaxy has a similar giant, a supermassive black hole anchored at the centre, shaping the galaxy's structure and evolution. These cosmic giants are not merely passive residents. They stir their surroundings, feeding on gas, launching jets of energetic particles, and leaving signatures that ripple across tens of thousands of light years. Their influence is subtle but profound, like the gravity of a mountain shaping the flow of rivers around it. Taken together, these discoveries, the abundance of planets, the staggering number of galaxies, the quiet presence of supermassive black holes, have reshaped our picture of the cosmos. It is no longer a universe of isolated lights in a dark emptiness. It is a vast, interconnected landscape, with structures that extend from the tiniest orbiting world to web-like arrangements of galaxies stretching across hundreds of millions of light years. There is something comforting about this shift. The universe feels larger, yes, but also more alive. Not alive in the biological sense, but alive in its constant motion, its hidden patterns, its quiet unfolding across scales far beyond our familiar reach. When you step outside tonight and look up, the stars you see are no longer solitary. They belong to a galaxy shaped by an unseen giant, and that galaxy is only one leaf on an enormous cosmic tree, one that branches into trillions upon trillions of shimmering lights. In the stillness of night, it becomes easier to let your thoughts drift outward along those branches, to imagine worlds orbiting other suns, to picture galaxies drifting across deep time, and to feel, if only for a moment, that you are part of something immeasurably large and quietly magnificent. If you imagine a galaxy from far away, perhaps from the vantage point of a quiet spacecraft drifting in the dark, you might picture a graceful spiral of stars slowly turning, like a silent whirlpool of glowing dust. The Milky Way, Andromeda, and thousands of others all share this elegant structure, arms curling outward, stars moving in great circular paths, and a soft glow that fades as you travel farther from the centre. For a long time, astronomers assumed that the motion of these stars would follow the same gentle rules familiar from our solar system, where the planets that orbit farthest from the Sun move more slowly, taking long, sweeping journeys around the centre. It seemed like a natural, orderly pattern, but in the middle of the 20th century, one scientist quietly began to uncover something that threatened that sense of order. Her name was Vera Rubin. At a time when women were rarely welcomed in academic observatories and often had to request access to telescopes in ways their male colleagues never had to consider, Rubin moved forward with patience and steady commitment. She wasn't searching for glory or for a theory that would rewrite the universe. She was simply trying to understand how galaxies turn. Working with her collaborator Kent Ford, who had helped develop a new kind of highly sensitive spectrograph, Rubin began measuring the speeds of stars at different distances from the centre of the Andromeda galaxy. The idea was simple. Stars near the centre should move faster, pulled by a stronger concentration of mass, and stars near the edge should move more slowly. That's what Newton's laws suggested, and that's what the tidy, familiar picture predicted. But the measurements refused to fit the picture. Rubin found that the stars far from the centre weren't slowing down at all. Instead, they were moving just as quickly as stars much closer in. It was as if the galaxy were spinning like a giant record, with every part moving at nearly the same speed. The outer stars were simply too fast, so fast that, by all conventional logic, they should have flown off into space long ago. Yet there they were, holding their paths with quiet certainty. There was only one explanation that made sense. Something invisible must be holding them in place, adding mass where none could be seen. Rubin's careful, repeated measurements gave weight to an idea that had been whispered about before, but never taken seriously on this scale. The galaxy, and indeed all galaxies, must contain far more matter than what glows in our telescopes. There had to be an unseen halo of something that didn't emit light, didn't interact with radiation, didn't shine, didn't absorb. Something that revealed its presence only through its gravity, dark matter. Rubin wasn't the first to suggest it, but her work made it undeniable. Her rotation curves, simple graphs showing star speeds plotted against distance, became some of the most important diagrams in modern astronomy. The curves were flat, not falling, like a road that refuses to slope downward no matter how far it stretches. Today, these curves are explained without symbols or equations by imagining the galaxy as a spinning disk suspended inside a much larger unseen sphere of mass. The luminous part, the stars, gas and dust, is only the glowing tip of a vast iceberg whose bulk remains hidden in the cosmic dark. This discovery changed almost everything that followed. If galaxies contain far more mass than we can see, then the universe itself must be built upon something invisible. The familiar stars and glowing nebulae become only a small fraction of the whole, and as astronomers refined their models, using cosmic surveys and gravitational lensing to trace how light bends around clusters, a picture emerged of a vast cosmic web, threads, filaments and nodes made of dark matter, stretching across hundreds of millions of light years. Galaxies lie along these filaments like dewdrops on a spider's web, held in place by the quiet pull of matter that never glows. Some theories propose that dark matter may come in a variety of forms, not just a single type of particle, a kind of dark zoo with species we have yet to identify. Others suggest exotic candidates, like black holes as small as atoms but as heavy as mountains, left over from the earliest moments after the universe formed. Experiments deep underground, like the large detectors that watch for the faintest signals, continue searching for these elusive particles. Some are tuning their instruments to catch tiny flashes that might reveal dark matter colliding with ordinary atoms. Others look outward, listening for hints in high-energy cosmic rays or patterns in how galaxies cluster. Despite the search, dark matter remains invisible, mysterious, and essential. Without it, the universe simply wouldn't look the way it does. Galaxies wouldn't hold together, clusters wouldn't form, the cosmic web wouldn't stretch across the void the way it does today. The structure of the universe depends on this quiet, unseen presence, a kind of scaffolding that supports the luminous parts we can actually observe. And yet, there is something beautifully gentle about this idea. The universe is held together not just by what we can see, but by what we cannot, by forces that don't shine or shimmer, but shape everything just the same. In a way, this invisible scaffolding is a reminder that the most important structures in life are often the ones we don't notice at first. The things that keep us steady, that hold our paths, aren't always visible. They may be subtle, quiet influences, relationships, memories, or hopes that guide us even when we're not aware of them. As we move onward, we'll begin to follow these invisible threads further, watching how they lead into discoveries that, in their own way, feel just as surprising and just as quietly transformative. There are moments in science when the universe feels almost playful, as if it waits patiently for us to become confident in our understanding, only to reveal that we have missed something essential. The discovery of the universe's accelerating expansion is one of those moments, quiet in the beginning, almost shy, and then world-shifting once the truth became impossible to ignore. It began with a simple question, almost a childlike one. Is the universe slowing down, or will it eventually stop expanding altogether? For decades, most astronomers assumed that cosmic expansion must be decelerating. Gravity, after all, pulls things together. If galaxies are moving away from each other because of the momentum left over from the Big Bang, then gravity should gradually slow that outward motion. Just like a ball tossed upward slows as it rises, the universe should steadily ease its expansion as it grows larger. That was the expectation, gentle, comforting, almost intuitive. In the late 1990s, two research teams set out to measure that slowdown with greater accuracy. Their tools were not rulers or test masses, but exploding stars, specifically supernovae known as Type Ia. These stellar explosions shine with almost the same brightness each time they occur, making them reliable cosmic beacons. By comparing how bright a supernova appears from Earth with how bright we know it ought to be, astronomers can estimate its distance. And by measuring the stretching of its light, they can estimate how fast the universe was expanding when the explosion occurred. It's a bit like looking back in time through candles placed at different distances across a long, dark hallway. Both teams, the High-Z Supernova Search Team and the Supernova Cosmology Project, began collecting data, measuring distances and redshifts with increasing care. Each new supernova felt like a small window opening into the distant past. At first, the data seemed routine. The early measurements matched expectations well enough, but then, gradually, a pattern began to emerge. a soft murmuring in the numbers that refused to align with the old picture. The supernovae appeared too faint, not faint because they were smaller or dimmer, but because they were farther away than they should have been if the universe's expansion was slowing down. The only explanation was unsettling in its simplicity. The universe must have been expanding more slowly in the past than it is now. In other words, expansion wasn't decreasing, it was speeding up. The universe was accelerating. When the first hints appeared, the scientists hesitated. Perhaps there were measurement errors. Perhaps dust obscured some of the light. Perhaps the intrinsic brightness of supernova varied more than everyone assumed. But as observations continued, the evidence piled up. The faintness wasn't an illusion. The pattern repeated again and again, across dozens of supernovae in distant galaxies. The teams compared their findings, scrutinized every assumption, and turned the data inside out. And after months of analysis, the only conclusion that survived was the one no one expected. The universe is not just expanding, it is being pushed apart faster and faster. This push had no obvious source. There was no roar of cosmic engines, no sign of any known force. Instead, the acceleration seemed to come from space itself, as if empty space possessed a quiet energy that grew more influential as the universe expanded. Scientists began calling this invisible influence dark energy, not because it was sinister, but because it slipped so easily beyond the reach of our instruments. Einstein had once added a term to his equations to keep the universe static, something he called the cosmological constant. He later dismissed it as his greatest mistake. But after the 1998 supernova results, that term suddenly seemed not like an error, but like a foreshadowing. Empty space might indeed contain a gentle pressure, a kind of soft push that becomes noticeable only when there is enough space for it to operate on. To understand what this means, imagine stretching dough. At first, when the dough is compact, your hands do all the work, but as it thins, the elasticity of the dough begins to pull itself apart more easily. In a similar way, the universe has grown so large that the subtle energy of space, barely noticeable billions of years ago, now influences the expansion more strongly than gravity does. This idea is strange, but it leads to a beautiful and haunting picture of cosmic history. For much of the universe's early life, gravity dominated. Galaxies pulled together, clusters formed, and immense structures took shape. But around 6 billion years ago, something changed. The density of matter diluted as expansion continued, but the energy of empty space remained constant. Slowly, quietly, it overtook gravity. The universe began accelerating, and the galaxies started drifting apart ever more rapidly. This discovery unsettled astronomers not because it violated physics, but because it revealed how much the universe had hidden behind its calm appearance. Even now, dark energy is not something we can touch or see. We infer its existence from the way galaxies move, the way space warps, and the way ancient light stretches across billions of years. It is subtle, like a breeze felt only through the motion of leaves. Yet the implications are profound. If acceleration continues, and current measurements suggest it will, distant galaxies will eventually slip beyond our cosmic horizon. Their light will stretch until it fades entirely. Over unimaginable spans of time, the night sky will slowly empty, leaving only the local cluster of galaxies bound together by gravity. Beyond that small island of stars, the universe will become darker, colder, and lonelier, expanding into silence. But that future is far beyond anything humanity will witness, and there is a kind of peace in that. The accelerating universe does not rush, it drifts. It expands with the gentleness of a rising tide. Its story unfolds not like a sudden revelation, but like a slow breath drawn across epochs. And in this breath lies a reminder. reality is not always what we expect, and sometimes the quietest forces shape the largest destinies. As we move deeper into the night, we'll continue exploring how this discovery intertwined with other mysteries, how the hidden structures of dark matter and the soft pressure of dark energy weave together the fabric of cosmic history. If you imagine the universe as a grand unfolding story, then dark energy is the quiet, persistent narrator, never seen, never heard, yet gently guiding the plot from behind the scenes. It doesn't rush, it doesn't shimmer, it doesn't call attention to itself. Instead, it leaves its fingerprints on the motion of galaxies, on the stretching of ancient light, and on the slow drift of the cosmic horizon. To understand dark energy is to understand not just what the universe is doing now, but what it has been doing for billions of years, and what it may do long after every familiar star has faded. When we think about the history of the cosmos, it's tempting to imagine everything happening quickly, with dramatic shifts and sudden changes. But most of the universe's life has unfolded patiently, almost lazily. For billions of years after the Big Bang, matter dominated the cosmic landscape. Galaxies condensed from primordial clouds, stars ignited in waves, lighting up the darkness. Gravity, simple and reliable, wove the structure of the cosmos like an invisible loom. During this long era, dark energy was present, but timid, its influence so faint that it barely mattered. You could think of it as a whisper lost beneath the roar of forming galaxies. This balance, however, was always temporary. As the universe expanded, matter grew thinner, spreading out like a mist, dissipating across a wide valley. Galaxies drifted farther apart, and the average density of matter dropped. Gravity's hold, once strong and authoritative, began to loosen. Meanwhile, dark energy remained steady, not thinning, not fading, just waiting. It doesn't dilute with expansion the way matter does. It keeps the same quiet pressure everywhere, no matter how large the universe becomes. And slowly, almost imperceptibly, its influence began to rise. Astronomers estimate that around 6 billion years ago, long before Earth existed, something subtle happened. Dark energy overtook matter. The tide turned, gently but decisively. Gravity no longer ruled alone. The universe began to expand faster than before, nudged outward by the soft push of space itself. Imagine a calm lake where the surface starts to ripple outward, not from wind, nor storms, nor stones, but from the lake's own depths. That is the strange heart of dark energy. It is the energy of space, not something added to it. To visualize how this affects the cosmos, picture two galaxies drifting apart. Billions of years ago, their motion was determined primarily by gravity. If gravity were the only force in play, you would expect their separation to slow over time. But that isn't what's happening. Instead, the distance grows more quickly now than in the past, not because the galaxies gain speed, but because the fabric of space between them is stretching more rapidly. It's a bit like two boats floating on an ocean whose tides are slowly rising. The boats aren't rowing away from each other, yet the distance between them grows. As dark energy continues to dominate, this stretching will only accelerate. Distant galaxies will drift farther and farther away, their light stretched until it becomes faint and cold. Over billions of years, entire clusters of galaxies, now visible through powerful telescopes, will slip beyond the cosmic horizon, a boundary defined not by walls or barriers, but by the speed at which space expands. Once they cross that horizon, their light will never reach us again. It isn't that they vanish, it's simply that the universe grows faster than light can traverse it. This process has an emotional weight. Imagine standing at a shoreline while the tide rises slowly, carrying distant lanterns farther into the night. At first, you might still see their glow. Then gradually the flickering becomes softer, dimmer until finally it fades into darkness. That is what dark energy does to the cosmic landscape, and yet, despite the melancholy of this image, there is a serenity to it. The universe isn't tearing itself apart violently. It isn't collapsing or combusting. It is drifting, steadily, quietly, with the patience of something that knows no rush. In the far future, countless trillions of years from now, the night sky will look very different from what we see today. The Milky Way and Andromeda will merge into a single galaxy, and nearby dwarfs will join them, forming a small island of stars gravitationally bound together. Beyond that island, the rest of the universe will fall into a silent darkness, too distant and too stretched for any light to bridge the gap. This concept is sometimes described as the long loneliness of the cosmos. But loneliness may not be the right word. The universe simply evolves. It breathes in its own rhythm, far slower than our minds can easily grasp. What feels like a loss from one perspective becomes, from another, a calm settling, a soft final chapter written in the quiet language of expansion. Some theories suggest even more dramatic endings. If dark energy grows stronger with time, the expansion might someday accelerate so rapidly that even galaxies, stars, planets, and eventually atoms would be pulled apart. Scientists sometimes refer to this idea with a name that sounds unsettling, but it's nothing more than a hypothetical scenario: the Big Rip. In that distant possibility, the universe would unravel like a tapestry, loosening its threads, each part drifting away from its neighbours until no structure remains. But this is only one idea among many, and the evidence so far points more gently toward a long, slow dimming, rather than a catastrophic tearing. For now, dark energy remains a mystery. We can describe its effect with remarkable precision, but the essence of what it is still escapes us. It could be a constant property of space, as Einstein once imagined. It could be a field that shifts slowly through time. It might even interact with matter in ways we do not yet understand. Every new observation offers a clue, but the picture is far from complete. What is clear, though, is that dark energy has shaped the universe's past and will shape its future. It orchestrates the grand, slow dance of galaxies. It guides the expansion of cosmic horizons. It sets the pace for the long twilight that awaits the stars. And somehow in the midst of all this, we find ourselves here, tiny observers on a small world, listening for the faint stories carried by ancient light. If you imagine the universe as a story written across time, then the rate at which that story unfolds is its tempo, its rhythm. Astronomers call this tempo the expansion rate, a gentle measure of how quickly galaxies drift apart. It's a simple idea at first glance, almost like watching two boats move away from the shore. But beneath that simplicity lies one of the most persistent mysteries in modern cosmology, a disagreement so stubborn that scientists refer to it as the Hubble tension. And like many quiet disagreements in nature, it begins not with noise but with measurements. The expansion rate of the universe is known as the Hubble constant. Rather than expressing it as symbols or hard numbers, you can think of it as a soft description. How much additional space forms between faraway galaxies with each passing moment? If two galaxies begin 1,000,000 kilometers apart, and the universe expands just enough to add an extra handful of kilometers over a certain span of time, that handful represents the Hubble constant. Scientists have refined ways to estimate this cosmic tempo for decades, using different methods that peer into different eras of the universe's history. The first method looks deep into the early universe, at light that has travelled for more than 13 billion years. This light, known as the cosmic microwave background, is a soft glow left behind from a time when the universe was young and hot. before atoms had even formed. By examining the delicate patterns in this ancient light, the tiny warm and cool spots frozen into it, scientists can infer how fast the universe must be expanding today. It's like listening to an echo in a canyon and using its tone and delay to understand the shape of the canyon itself. The second method looks at the opposite end of time, the nearby universe filled with galaxies whose light is only slightly stretched by expansion. This approach relies on a series of distance markers such as pulsating stars and bright supernovae. Like candles placed at known distances, their brightness becomes a guide for mapping how fast galaxies are receding right now. It's a modern cosmic version of surveying, where astronomers combine layers of measurements to build a ladder of distances stretching outward through space. Both methods are refined, elegant, and built on decades of careful work, yet they do not agree. The early universe method, using ancient light, suggests one expansion rate, while the late universe method, using nearby galaxies, suggests a noticeably faster pace. Imagine two clocks that have always kept time perfectly, but now, for reasons unknown, begin to tick at slightly different speeds. Each clock is built with precision, each is measured with care. Yet the disagreement persists, quiet but undeniable. At first, scientists suspected a small oversight. Perhaps some of the young stars used as distance markers behaved differently than expected. Perhaps the ancient light carried tiny distortions that were misunderstood. Perhaps gravitational influences along the path of the light were complicating the results. But as more data arrived, cleaner, sharper, meticulously checked, the disagreement grew sharper rather than softer. This is the Hubble tension, a stubborn mismatch between two well-tested ways of measuring the universe's expansion. And what makes it so intriguing is that both methods are internally consistent. Each approach is like a well-played piano piece. Every note in the sequence sounds right on its own. Yet when played together, the two melodies don't harmonize. The tension doesn't mean that the universe is broken or that physics has failed. Instead, it suggests that something deeper may be waiting to be uncovered. The universe might be whispering about a new ingredient in its makeup, or a subtle shift in its behavior over time. Some scientists propose that dark energy may change slowly across cosmic history, like a breeze that grows stronger or softer as time passes. Others imagine a kind of early universe influence that has left a faint imprint on the cosmos, altering the rhythm of expansion in ways that are only now becoming detectable. There are even ideas that hint at hidden physics, phenomena just beyond the reach of current theories. Some imagine the existence of new light particles created in the early universe, gently influencing its growth. Others consider the possibility that gravity itself might behave differently on the larger scales, bending the cosmic landscape in ways that neither classical nor quantum theory has fully captured. Despite the profound nature of these questions, the tone of the discussion among astronomers is not frantic. It is patient, reflective, and deeply curious. The Hubble tension is viewed less as a crisis and more as a quiet doorway. One of those rare thresholds in science where every careful step leads towards something unknown but promising. To picture the tension in a gentle way, imagine standing at the edge of a forest where two paths begin. Each path has been carefully mapped, walked many times, and trusted. Yet when you follow them both out to their far ends, they don't meet where they should. The forest hasn't changed, and the paths are not broken. But something in the terrain is different from what anyone expected, and that difference, once understood, may reveal that the forest is wider and more intricate than your old maps ever showed. As new telescopes prepare to survey the sky with unprecedented precision, giant observatories with enormous mirrors and delicate detectors The hope is that fresh data will clarify this mismatch. Perhaps both clocks will eventually tick in unison once new measurements correct the assumptions behind them. Or perhaps they will grow further apart, revealing a deeper pattern that has been hidden until now. Either outcome would be a gift. Agreement would strengthen our confidence that we understand the large-scale workings of the cosmos. Disagreement would point to an undiscovered chapter in the story of the universe, one that might reshape our understanding of dark energy, cosmic structure, or the very fabric of space and time. For now, the Hubble tension remains a quiet puzzle, humming softly beneath the surface of cosmology. It doesn't interrupt the universe's grand unfolding, but it changes the way we listen to the cosmic rhythm. And sometimes it is precisely these off-notes, these gentle mismatches, that lead to the most beautiful discoveries. If you imagine shrinking yourself down, not physically but in imagination, smaller and smaller until atoms look like enormous balloons drifting in the dark, you would eventually reach a realm where the ordinary rules of the world begin to soften. Here, things do not behave like pebbles or marbles or anything your hands can hold. Instead, they act like whispers of possibility. This realm is the quantum world, a place where certainty dissolves into gentle maybes and where reality seems to shimmer between many forms at once. For most of human history, people believed that the universe worked like a clock, precise, predictable, and governed by fixed rules. If you knew how something was moving and how strong the forces on it were, you could predict exactly where it would be in the future. This idea felt safe. It gave the universe a sense of solidity, a kind of reassuring structure. But in the early 20th century, the smallest pieces of nature began to rebel against that certainty. Light, which had long been understood as a wave, sometimes behaved like a particle. Electrons, which seemed like tiny balls, sometimes spread out like ripples on water. Experiments revealed patterns that could not be explained by classical rules. When scientists tried to observe electrons passing through narrow slits, the electrons didn't travel like bullets. They formed interference patterns, as if each electron passed through both slits at once. It was as though nature was gently telling us that the world is more subtle than our everyday senses allow. The framework that eventually explained these strange behaviours is quantum mechanics, a name that sounds sharp and technical, but at its heart, simply describes how the universe behaves at its smallest scales. In this realm, particles do not sit in specific places or follow single paths. Instead, each particle exists as a cloud of possibilities, described not by a precise location, but by a soft distribution of where it could be. You can think of it like a faint mist drifting through a room, with some corners more likely than others, but no single point where the mist must be. This idea is known as the wave of probability, but rather than imagining sharp symbols or dense formulas, picture a gentle glow spread through space, brighter in some regions, dimmer in others, indicating the likelihood of finding the particle there. When you look for it, the glow seems to collapse to a single spot, as if the universe quietly chooses one of its many possibilities in the moment of observation. One of the most surprising conclusions of quantum mechanics is that empty space is never truly empty. Even in total darkness, even when every atom has been removed from a region, the vacuum still swirls with activity. Tiny pairs of particles flicker into existence and fade away again, lasting only for brief instants. These flickering presences are not ghosts or illusions, they are expressions of the quantum fields that permeate all space. You could think of them as the universe breathing gently at the smallest scales. As strange as this world seems, its principles are woven into everyday life. Every chemical bond, every spark of electricity, every beam of light in your home arises from quantum behaviour. Atoms are stable, because electrons, those shimmering clouds of possibility, are allowed to occupy only certain patterns around a nucleus. Without the quantum rules that restrict and guide them, matter as we know it could not hold together. Some of the deepest strangeness in quantum mechanics comes from the way reality resists being pinned down. In ordinary life, you can pick up a stone and know exactly where it is. In the quantum world, trying to measure one property precisely makes another property blur. If you measure a particle's position very sharply, its motion becomes uncertain. If you measure its motion clearly, its position becomes vague. This is often called the uncertainty principle. But instead of imagining it as a forbidding restriction, picture it as a gentle truth. The smallest things cannot be known with complete clarity, because they are not fixed objects. They are patterns that shift depending on how you look. The real turning point came when scientists realized that these probabilities were not simply ignorance, like not knowing which card lies face down on a table, but something more fundamental. Reality at the tiny scale does not take on a definite form until we observe it. Before that, it holds many possible futures at once, like branches of a tree that have not yet decided which direction to grow. To give a soft analogy, imagine a coin spinning in the air. While it spins, it is neither heads nor tails, but a shimmering blend of both possibilities. Only when it lands does it reveal a definite state. In the quantum world, particles remain in that shimmering state until interacted with. This idea is called superposition, and though it defies intuition, it lies at the heart of everything from electron behavior to the workings of future quantum computers. Even more surprising is that particles can become connected in a deeply intimate way, sharing a single combined state no matter how far apart they drift. This phenomenon is known as entanglement. If two particles become entangled, measuring one instantly reveals something about the other, even if they are separated by vast distances. It isn't that information travels between them, nothing moves faster than light, but rather that the two particles are no longer independent. They form one extended system, like two dancers performing a perfectly coordinated routine even when placed on opposite sides of a quiet stage. Einstein once referred to this as spooky action at a distance, but modern experiments confirm that entanglement is real. Photons sent through fiber optic cables or through open air remain correlated across miles. In principle, this coordinated behavior could extend across the galaxy, or even farther if the entangled particles could be carried that far. The universe, at its smallest levels, may be knit together in ways that feel almost poetic. Threads of shared existence stretching across unimaginable distances. And yet, despite the profound implications of quantum mechanics, the world it describes is not chaotic or wild. It is precise, consistent, and elegant. The probabilities follow patterns. The waves of possibility evolve smoothly. The uncertainty is not confusion. It is structure. The quantum realm is more like a soft field of possibilities than a jumble of unpredictability. As we drift deeper into this journey, we will explore how these quantum foundations connect to the wider universe, shaping the matter between stars, the glow of galaxies, and even the way time itself unfolds. For now, it is enough to rest in the knowledge that beneath everything we see lies a world woven of delicate chance, quiet patterns, and the gentle breath of possibility. If you think back to childhood, you might remember moments when your imagination blurred the lines between possibilities, when a shadow in the corner could be many things at once, or when a coin spinning on the table seemed to hold both of its faces before settling gently onto one side. In the quantum world, nature behaves in a way that echoes that same sense of suspended possibility. But unlike childhood impressions, these behaviors are not illusions, nor tricks of perception. They are woven into the foundation of physical reality, guiding the movement of the smallest particles with a quiet, unwavering logic. The first of these behaviors is superposition, a word that may sound technical but simply means that a single system can hold many potential states at the same time. Imagine a tiny particle, not a pebble or a grain of sand, but something far smaller, something that behaves more like a whisper than an object. Instead of sitting firmly in one place or moving along a single path, this particle spreads out like the faint glow of a lantern in fog. It occupies a range of possibilities, each one gently overlapping with the next. Before anyone observes it, the particle doesn't choose a definite state. It remains suspended among possibilities, like that coin spinning in the air before settling. This is not a metaphor. Quantum experiments show it again and again. A particle in superposition truly behaves as though it carries multiple futures at once. To picture this softly, imagine tracing your finger across the surface of a pond. The ripples that form do not mark a single path. They spread, intersect, overlap. The particle is something like that, a ripple of potential, not confined to a single point until it encounters something that forces it to take a definite shape. The second behavior, entanglement, is even more astonishing. It begins when two particles interact in a way that causes their states to become linked, as if their possibilities are stitched together. After this moment, no matter how far apart they drift, meters, kilometers, or even light years, their connection remains. If you observe one particle and find that it settled into a particular state, the other particle settles simultaneously into a complementary one. This does not mean that information travels between them in any forbidden way. It means, more subtly, that they are no longer separate. They share a single, unified description, as if they are two notes of a single chord. To hold this idea gently, imagine two musical instruments tuned so precisely to each other that when one plays a note, the other resonates with the same tone, even if placed on opposite sides of a quiet room. Or imagine two clocks that, for reasons hidden from ordinary sight, keep such perfect time together that checking one instantly tells you the time on the other, no matter how far away they have been carried. Entanglement is not communication, it is correlation, a deep, structural connection that arises not from signals exchanged, but from a shared origin. Quantum experiments continue to reveal this connection with remarkable clarity. Pairs of photons, particles of light, are created in special crystals and sent along different paths, sometimes through long fiber optic cables, sometimes through the open air between mountain peaks. No matter how separated they become, their measurements remain locked together, displaying a harmony that cannot be explained by classical ideas. Some experiments have even linked entangled particles over hundreds of kilometers, confirming that the bond between them does not weaken with distance. This might feel like magic, but it is profoundly real, confirmed through tests so delicate they measure subtle patterns in the flickering of light. Yet the emotional impact of this phenomenon often lands more softly than the technical details. Entanglement suggests that the universe is more connected than our everyday intuition would ever guess. Not connected by wires or waves, but by patterns. Patterns that stretch across space like invisible threads. In a sense, the quantum world whispers that separateness is not absolute, that even distant things can share a single pulse of existence. When you think about superposition and entanglement together, a larger picture emerges. The quantum world is not built from tiny rigid objects. It is built from relationships, between possibilities, between particles, between the act of observing and the way things unfold. A particle's behavior depends not only on where it is, but on what else it is woven together with. Reality at the smallest scale becomes less of a collection of isolated dots and more of a gentle tapestry, each thread influencing the others in ways we cannot always see. This picture may feel abstract, but it connects deeply with the world you know. Every atom in your body, from the oxygen you breathe to the carbon that anchors your cells, is shaped by superposition. Electrons hold their patterns around nuclei because they occupy many potential orbits at once, forming stable grounds for chemistry to flourish. Every interaction between light and matter, every glow of a lamp or flicker of a screen, carries the quiet signature of entangled interactions between particles created and absorbed. Even the warmth you feel when sunlight touches your skin is the result of quantum laws, because photons do not simply strike atoms. They enter into patterns of possibility with them, exchanging energy in discrete, carefully orchestrated steps. This might sound complex, but you can think of it like a dance between particles, each movement guided by the rhythm of quantum rules. The dance is sometimes soft, sometimes sharp, but always governed by patterns that are both beautiful and strange. Superposition and entanglement are often described as the most mysterious behaviours in physics. Yet when approached gently, they feel less like puzzles and more like quiet truths. Truths that remind us that the universe is far more subtle than it appears at first glance. They teach us that certainty is rare at the smallest scales, that relationships matter more than isolation, and that even the simplest particles carry a kind of delicate grace. As we move forward, we will begin to see how these quantum ideas are not distant curiosities, but practical foundations of modern life. They power the technologies that shape our world, from the lasers that form the backbone of communication to the tiny switches that store the world's information. And beyond that, they hint at a future where even more wondrous devices become possible, machines that harness not just matter and energy, but the very patterns of information woven into the quantum realm itself. If you were to look around your room right now at the soft glow of a lamp, the gentle hum of your phone charging, or the screen you're using to listen to this, you might not suspect that beneath all of these quiet, familiar comforts lies a world of deep quantum behaviour. We often imagine quantum physics as something remote, tucked away in laboratories filled with shimmering wires and superconducting magnets. But the truth is much gentler and much closer. Quantum rules are the invisible grammar of the modern world, shaping everything from the way light behaves to the way information flows. Without these rules, the technologies we depend on every day would simply not exist. To see this clearly, it helps to start with one of the most elegant inventions rooted directly in quantum mechanics, the laser. The word comes from a long phrase about light amplification, but the idea is much simpler to picture. Imagine a choir where every singer is perfectly in tune, every voice rising and falling at the same pitch, forming a sound so pure it feels like a single note. A laser is light behaving in that same perfect harmony. In ordinary light, like the glow from a bulb, billions of photons rush out at different times, in different directions, each with its own slightly unique personality. But in a laser, photons move as one, a unified beam that can travel miles without losing its shape. This extraordinary coherence is only possible because of a quantum process known as stimulated emission. Instead of describing it with symbols or complicated terminology, picture a row of musicians waiting for the right cue. When one photon passes through an excited atom, it gives a gentle nudge, encouraging the atom to release another photon in perfect unison. Same direction, same energy, same rhythm. This growing wave of synchronized light creates a beam so pure that it can cut through metal, carry data along fiber optic cables, or help surgeons perform delicate operations with almost unimaginable precision. Every time you see a laser pointer trace a simple red dot across a wall, you're watching a quantum chorus perform with breathtaking coordination. Another quiet marvel of quantum physics is the transistor, the tiny switch at the heart of all computing. Your phone, your computer, your TV, every digital device you've ever touched relies on billions of these switches, flipping on and off like microscopic gatekeepers of information. And at the core of each transistor lies a quantum truth born from the behavior of electrons in matter. Electrons don't move like marbles through tubes. They flow more like soft waves through landscapes of energy, slipping between patterns in ways governed by quantum rules. The ability to control this wave-like behavior inside tiny layers of silicon is what allows a transistor to switch with unimaginable speed, millions or billions of times each second. If the world feels fast today, it is because quantum mechanics silently keeps the rhythm. Even navigation, guiding planes, ships, delivery routes, and the map on your phone relies on quantum rules. The Global Positioning System, or GPS, depends on clocks so precise that they can measure time down to trillionths of a second. These clocks are anchored in quantum phenomena inside atoms, where electrons leap between energy levels with perfect regularity, like tiny pendulums glowing with rhythm. The frequency of this glow becomes a timekeeper, far more stable than any mechanical clock could ever be. If these quantum clocks ran just a fraction of a second too fast or too slow, GPS locations would drift by miles each day. Your phone knows where you are because quantum mechanics keeps time with extraordinary care. Even temperature, the warmth in the air, the heat from your laptop, has its roots in quantum behavior. Atoms vibrate with tiny energies that can only increase or decrease in small, thick steps. These gentle steps, these tiny packets of movement, help explain why materials heat up, cool down, conduct sound, or insulate against it. When you warm your hands around a cup of tea, quantum vibrations ripple through the ceramic, carrying heat outward like a quiet orchestra playing an invisible song. Some elements of daily life rely even more directly on quantum rules. The flash memory in your phone stores information using the ability of electrons to tunnel through barriers, something that would be impossible in classical physics. From the outside, it looks like a simple chip, but inside, tiny landscapes of energy allow electrons to slip across boundaries in ways only quantum mechanics permits. The device remembers your photos, your notes, your contacts, all because of the way particles obey these subtle rules. Even colour itself, why a leaf looks green, why the sky glows blue, why a sunset softens into orange, is shaped by quantum interactions between light and matter. When sunlight touches your surroundings, electrons absorb certain wavelengths and let others pass or reflect. These decisions aren't arbitrary. They follow patterns set by quantum energy levels, quiet rules that decide which colours bloom and which fade. Without quantum structure, the world would not have its familiar palette. It would be a place of washed-out greys, stripped of the delicate hues that make evenings warm and mornings gentle. And in the heart of your body, quantum processes play an even more profound role. Every chemical reaction relies on probability clouds around electrons, shaping the bonds that form and break in your cells. Your metabolism, your senses, the signals passing between neurons, all of these dances depend on quantum rhythms. You are, in a very literal way, a macroscopic pattern built from microscopic uncertainties. What makes all this especially soothing is that quantum mechanics, despite its apparent strangeness, is not chaotic. It does not inject randomness into your life in any violent way. Rather, it sets the stage on which matter performs its delicate routine. It is the quiet choreography that underlies everything you see and touch, the subtle foundation without which modern civilization could not stand. If lasers are choirs of light, and transistors are tiny wave-guided switches, then you could think of the quantum world as the hidden conductor. Not a conductor who shouts or gestures wildly, but one who guides with small, consistent cues. A conductor whose presence you never see, but whose influence you feel every moment you interact with technology, warmth, touch, or light. In the next step of our journey, we'll move from the quantum foundation of everyday objects to the quantum foundation of something more abstract but equally essential, our sense of time itself. Because the same delicate rules that guide light and matter also guide the ticking of the universe, allowing us to measure time with extraordinary precision, as if listening to the softest heartbeat woven into the fabric of reality. If you close your eyes for a moment and imagine time not as numbers on a clock but as a gentle river, you might picture its flow as smooth and steady. Yet time does not move the same for everyone or everywhere. It flows at slightly different speeds depending on gravity, motion, and even height above the ground. These differences are far too delicate for human senses to notice, but the universe feels them. And today, with the help of quantum mechanics, so do we. We can listen to time with instruments so sensitive that they detect variations smaller than a heartbeat, smaller than the flutter of a wing, smaller than anything the world once believed measurable. The idea of defining time through light began with a simple principle. Atoms behave with perfect regularity. Inside certain atoms, like cesium, which has become the quiet workhorse of modern timekeeping, electrons shift between energy levels with a rhythm so steady that it forms a natural clock. Each shift produces or absorbs light at a frequency that never wavers, a kind of tiny glowing heartbeat. Instead of counting seconds through the swing of a pendulum or the vibration of quartz crystals, atomic clocks count these microscopic pulses of light. And because the pulses are incredibly fast, billions of gentle beats every second, they allow us to measure time with astonishing precision. You can think of the cesium atom as a small lantern inside a perfectly silent room. Each time its electrons hop from one pattern to another, they emit a faint flash of light. The clock listens to these flashes, counting them carefully. When it reaches a certain number, specifically around 9 billion beats, it declares that 1 second has passed. We never need to speak the number. Instead, we can imagine it as a steady hum, a rhythm that never slips or wanders. But technology did not stop with cesium. Researchers then built optical clocks, using atoms such as strontium or ytterbium that vibrate at frequencies far higher, like small strings being plucked at unimaginable speeds. These vibrations occur hundreds of thousands of billions of times each second. To make that sound soft enough for bedtime, you can imagine each atom as a tiny violin string tuned to an incredibly high pitch, one so pure and unwavering that it outperforms any musical instrument ever crafted. Listening to these strings gives scientists a measure of time so sharp that they can detect a difference in the flow of time between 2 points separated by just a few centimeters, about the height of a stack of coins. This sensitivity reveals a remarkable truth. Time flows more slowly closer to Earth's surface, where gravity is slightly stronger, and more quickly higher up, where gravity gently loosens its hold. It's a quiet echo of Einstein's insight that gravity bends time, causing it to stretch or compress depending on the strength of the gravitational field. In soft language, time is like a slow river that deepens near heavy masses and becomes shallower as you drift upward. Atomic clocks are the instruments that let us hear these subtle changes in the current. In laboratories around the world, scientists have measured time differences caused by raising one clock just a few millimeters above another. Imagine placing 2 tiny violins on a table, one slightly higher than the other, and hearing that the higher one plays its note just a touch faster. The difference is so small that if you relied on mechanical clocks, you would never detect it. But quantum clocks hear the shift like a faint whisper in an otherwise silent night. These capabilities don't just refine our philosophical understanding of time. They shape essential technologies. GPS satellites orbit Earth high above the surface, where gravity is weaker and time flows faster. Without adjustments based on quantum-calibrated time dilation, your phone's location would drift by kilometers every day. The reason your map can guide you through winding streets is because tiny clocks inside satellites constantly correct for the gentle stretching and compressing of time as they move through space. Atomic clocks also let us measure changes in Earth's gravitational field. As groundwater levels rise or fall, as ice melts or accumulates, gravity shifts ever so slightly. Quantum clocks can listen to these changes, hearing them as variations in time's rhythm. In the future, entire networks of such clocks may help track climate patterns, monitor volcanic activity, or detect quiet shifts in the crust long before earthquakes occur. But perhaps the most poetic aspect of these clocks is how they reveal time not as a rigid backdrop, but as something alive and responsive. They show that time bends in the presence of mountains, slows inside deep mines, and hastens at mountaintops. They show that even your head ages ever so slightly faster than your feet because it sits farther from Earth's centre. These differences are tiny, a few trillionths of a second over a lifetime, but they are real. The quantum tools we have built simply make it possible to hear them. Imagine walking through a quiet gallery of clocks, each tuned to a slightly different height. The ones near the floor tick just the slightest bit slower. The ones above tick faster, as though catching more of the universe's outward breeze. Together, they form a soft symphony, revealing the contours of time as it bends and sways around invisible forces. In a way, atomic and optical clocks have taught us that time is not a universal rhythm, but a collection of local melodies woven into a grander song. Each location in space sings its own tempo. Gravity conducts the deeper notes, motion adds faint harmonies, and the quantum behavior of atoms provides the instruments, the violins, lanterns, and humming strings, that let us listen to these melodies with exquisite clarity. As we drift onward, we'll soon encounter another kind of measurement made possible by quantum precision, one that allows us to hear something even more extraordinary, the faint passing tremors of space-time itself. If you imagine space not as an empty stage but as a soft, flexible fabric, then you can begin to picture one of the most delicate phenomena ever detected: gravitational waves. These waves are not ripples on water or vibrations in air. They are tremors in the fabric of space-time itself, tiny stretches and squeezes that travel across the universe, carrying stories from distant, violent events. For most of human history, these tremors passed by unnoticed, slipping quietly through the earth, the oceans, the mountains, even through you, without leaving a trace. But now, thanks to instruments built with extraordinary care, we can listen to them. And what we hear is the universe ringing like a distant cosmic bell. To understand gravitational waves gently, imagine placing a heavy ball on a stretched blanket. The ball makes a dip, curving the fabric downward. If you move the ball abruptly, the blanket shivers with ripples radiating outward. In the real universe, objects like stars and black holes sit on the fabric of space-time, bending it with their weight. When they move in certain ways, especially when two of them orbit and crash together, they send out waves that ripple across the cosmos. These waves are unimaginably small by the time they reach us. When two enormous black holes collide somewhere in a distant galaxy, the resulting trembling of space-time that sweeps past Earth may stretch and compress distances by a fraction so tiny, it would be like changing the length of a 4-kilometre tunnel by less than the width of a proton. Yet detecting this impossibly faint shift is exactly what the LIGO observatories have achieved. LIGO, the Laser Interferometer Gravitational Wave Observatory, relies on a simple idea made incredibly sensitive. Imagine two long tunnels arranged like the arms of a giant letter L. At the end of each tunnel is a mirror. A laser beam is split into two halves, each one travelling down a different arm, bouncing off the mirrors and returning to meet at the centre. If the arms are exactly the same length, the returning beams align perfectly, like two waves that crest and fall together. But if a gravitational wave passes through Earth, it will stretch one arm ever so slightly while squeezing the other, causing the two beams to fall out of step by the tiniest fraction imaginable. That tiny misalignment becomes the signature of a space-time tremor. This method is called interferometry, but instead of hearing that word mechanically, think of it as listening for the softest possible echo inside a cathedral. The laser beams form a kind of delicate tuning fork. When space-time itself vibrates, even by a whisper, the tuning fork's tone changes, revealing the presence of the wave. The first confirmed detection came in September 2015. It was marked by a file name that looks technical on paper, but we can speak it softly as the first gravitational wave event observed in 2015. On that day, LIGO caught a faint rising chirp, a small increase in frequency over a fraction of a second. That chirp was the sound of two black holes spiralling into each other more than 1 billion light-years away. As they approached, they moved faster and faster, dragging space-time into a tightening whirlpool until they collided, releasing more energy in that instant than all the stars in the observable universe emit together. Yet because that energy radiated as gravitational waves, its arrival at Earth produced a tremor so tiny that only LIGO's carefully tuned instruments could hear it. To picture this gently, imagine two enormous bells made of darkness colliding in the night and sending out a wave that shivers through the cosmic fabric. That shiver reaches us after travelling across billions of years, long after the bells themselves have merged into a single, silent mass. We are listening not to the bells, but to the faint echo of their meeting carried across the universe. What makes gravitational waves especially beautiful is that they bring us information we could never obtain through light alone. Telescopes show us what the universe looks like. Gravitational waves tell us how it moves. Light can be absorbed, scattered, or blocked, but gravitational waves pass through matter effortlessly. They carry memories of events hidden from ordinary view, like the mergers of black holes, the collisions of neutron stars, and perhaps one day, even faint whispers from the earliest moments after the universe began. After that first detection, the field blossomed quickly. More events followed. Additional black hole mergers, then collisions of neutron stars that lit the sky with a burst of heavy elements. Gold, platinum, and others formed in the chaos. Observatories around the world coordinated their instruments, combining visual light, X-rays, radio waves, and gravitational waves into a single symphony of observation. For the first time, humanity observed a cosmic event through multiple senses at once, like seeing lightning and hearing thunder together after a lifetime of only seeing the flash. To explain the sensitivity of these instruments softly, picture trying to measure the distance between two distant mountaintops and being able to tell whether they change by less than the width of a single hair. Or imagine stretching your arms wide and noticing a change in that span equal to a fraction of the size of a single atom. Quantum mechanics plays a quiet role here too. The laser beams in LIGO are stabilized using quantum techniques that reduce the noise created by the light itself, helping scientists hear the faint tremors more clearly. It is a gentle blending of two worlds, quantum precision and cosmic scale events. As future observatories come online, some floating in space, others buried deep underground, we will hear even more subtle vibrations. the soft rumble of supermassive black holes merging in the centres of galaxies, the echoes of stars collapsing, perhaps even signals from the universe when it was only a heartbeat old. Each new detection is a reminder that the cosmos is not silent. It hums, resonates, and rings with the memory of colossal motions, all carried through the quiet fabric of space-time. Gravitational waves extend our senses in a way that feels almost intimate. They are not flashes of light or particles striking detectors. They are the universe itself shifting, breathing, rumbling in ways that reach us long after the events that caused them have passed into darkness. And in listening to these tremors, we participate in a kind of cosmic eavesdropping, one that lets us hear what no eyes could ever see. As we drift forward, our journey will take a turn toward the future, toward machines built not just to sense the quantum world but to harness it directly. Machines that process information through the same delicate patterns that shape reality itself. When you think of information, you might imagine something simple. A light switch that is either on or off, a bead on an abacus moved to one side or the other, a coin placed heads or tails on a table. Classical computers, every laptop, phone or server operate using this kind of information. They're built from tiny switches, each one holding a single definite state, yes or no, 1 or 0, on or off. It is a solid, dependable way of storing knowledge, a stable foundation on which modern computing has grown. But in the quantum world, the smallest units of information behave differently. They do not settle into neat categories or rigid alternatives. Instead, they spread into possibilities. They blend. They overlap. A quantum bit, a qubit, is not a switch that must choose between on and off, but a soft, delicate system that can hold many potential states at once. It is like a coin spinning gently in the air, embodying heads, tails, and all the shimmering combinations in between until it touches the table. To understand qubits softly, imagine a small sphere, smooth and glowing faintly. A classical bit would occupy a single point on the surface, either the North Pole or the South Pole, corresponding to its two definite states. A qubit, however, can rest at any point on that sphere, not forced into extremes, but allowed to drift in an infinite range of mixtures between them. This shape is often used in science to describe a qubit state, but instead of thinking of it as geometry, you can picture it as a dawn sky, shifting gradually from night to day, holding many hues at once before settling into full morning light. This ability to hold multiple possibilities simultaneously is the essence of superposition applied to information. When a qubit is placed into superposition, it carries not one value but a softly layered blend of what could be. And the moment you add more qubits, something extraordinary happens. In classical computing, 2 bits can hold only 4 combinations, off, 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 on, off, on. But 2 qubits in superposition can hold a gentle cloud of all 4 possibilities at the same time. Add a 3rd qubit, and the number of possible states doubles again. Add a 4th, and it doubles yet again. After 20 qubits, the number of overlapping possibilities becomes so vast that if you tried to list them, you would run out of space long before you reach the end. In soft terms, the possibilities grow like a sea expanding outward, doubling its shoreline each time a new qubit is added. Researchers sometimes say, a system of qubits holds 2 raised to the number of qubits potential configurations. Instead of stating that sharply, you can think of it as a quiet ocean whose surface area keeps doubling with each new ripple. Of course, this sea of possibilities is only useful if we can guide it, if we can coax the qubits into weaving patterns that help us solve problems too complex for ordinary computers. And this is where entanglement returns as a central character in our story. When qubits become entangled, they no longer behave like separate coins or separate spheres in the dawn sky. They behave as parts of one extended system. Changing one changes the whole pattern. You can think of entanglement among qubits as threads binding them into a single fabric, so that a touch on one corner sends a gentle tremor through the entire weave. With entanglement, quantum computers become more than collections of individual possibilities. They become orchestrated fields of possibility, like a choir of voices singing in harmony, each note shaped by the others. While classical computers process one combination at a time, a quantum computer can explore many combinations simultaneously, allowing it to solve certain problems more efficiently. Not all problems, of course, but some, like simulating the behavior of complex molecules or searching for patterns in vast landscapes of data, become far more approachable when treated as waves of possibility rather than rigid steps. This parallelism can sound overwhelming, but in practice, it is guided by careful sequences of operations, soft rotations and gentle nudges that shift the pattern of possibilities until the right answer becomes more likely than the others. When the system is finally observed, the quantum wave of possibilities collapses into a definite outcome, like the coin landing after a long spin. The challenge lies in shaping that wave before it settles, encouraging the correct outcome to become the most natural one. One of the most graceful ways to imagine quantum computation is to picture overlapping waves on a calm lake. Each wave represents a different potential solution. When you design the right quantum operations, the waves that correspond to wrong solutions interfere with each other, cancelling out gently, like ripples fading as they meet. Meanwhile, the waves for the correct solution reinforce each other, growing stronger until that solution becomes the one revealed when the final measurement occurs. This is why qubits are not merely faster bits. They follow a completely different logic, a logic of gentle superpositions, woven correlations, and interference patterns. Classical computers march forward step by step, checking one path after another. Quantum computers explore many paths at once, letting the structure of the problem guide the interference of waves. Sometimes the difference is like walking a maze with a lantern versus letting the entire maze glow softly, so all the paths become visible at once. To bring this closer to everyday life, imagine trying to find a single key in a drawer filled with thousands of similar ones. A classical search would require checking each key individually. A quantum search, handled with the right algorithm, would treat all the keys as part of a single shimmering pattern, allowing the correct key to emerge far more quickly because its pattern stands out among the others. Another gentle analogy is to think of qubits as dancers on a vast stage. Each dancer begins with a range of possible steps. As the music plays, the music being the quantum operations, the dancers coordinate their movements through entanglement. Wrong choreographies fade, right ones strengthen, and by the final moment the stage reveals a single coherent performance, the answer. What makes all this so mesmerizing is that it is not theoretical speculation. Laboratories around the world now host small quantum processors, tiny chips cooled to near absolute zero, where qubits made from superconducting loops or trapped ions perform delicate dances of possibility. They are not yet powerful enough to outperform classical computers on most tasks, but they demonstrate the principles that future systems will build upon. As we drift into the next part of the journey, this story will grow more physical. We will step inside the quiet chambers where qubits are kept cold and still, where machines hum softly at temperatures colder than deep space. There, we will see how quantum computers are constructed, not as monolithic engines, but as delicate instruments that require silence, calm, and careful protection from the noisy world. If you picture an ordinary computer, you might imagine a warm, humming box on a desk, filled with circuits, electricity, and the soft whir of cooling fans. A quantum computer, however, lives in a completely different world. It is not warm, is not loud, it is not housed inside a simple metal frame. Instead, it exists inside an intricate tower of nested cylinders that look almost like a chandelier of golden plates, wires, and shimmering loops. And rather than being warmed by electricity, it is kept colder than any natural place in the universe, colder than deep space, colder than the shadowed craters of distant moons, colder even than the faint glow left over from the birth of the cosmos itself. This extreme cold is not a stylistic choice. It is essential because qubits, the delicate building blocks of quantum computers, are incredibly sensitive. A whisper of heat, a stray vibration, even a faint electrical disturbance can cause a qubit to lose its quantum character. When this happens, its graceful superposition collapses, its correlations unravel, and it drifts back into the simple, definite behavior of ordinary matter. To protect qubits from this fate, scientists place them inside elaborate cooling systems called dilution refrigerators. Instead of thinking of this device as machinery, imagine it as a series of quiet, nested chambers. Each chamber sits inside a colder one, like a set of Russian dolls carved from frost. The deepest chamber, where the qubits live, is kept just a few thousandths of a degree above absolute zero. In soft language, that temperature is less than 2/100ths of a degree above the coldest possible temperature in nature. At this point, heat barely moves at all. It is as if the atoms themselves have fallen into a nearly perfect stillness, allowing the fragile quantum patterns to survive without being shaken apart. Inside this silent heart, qubits take different forms depending on the technology used. Some are made from superconducting loops, tiny circuits where electric current flows without resistance. You can picture these loops as small racetracks where electrons glide endlessly, moving in patterns that represent quantum states. Others are formed from single ions, atoms missing one electron, held in place by gentle electromagnetic fields. These trapped ions float above the surface of a chip like tiny beads, suspended in still air, manipulated with beams of laser light so precise that they shift the ions' internal rhythms without disturbing the world around them. Working with qubits is a little like handling soap bubbles in a quiet room. One wrong move, a vibration, a pulse of heat, a stray magnetic field, and the shimmering structure bursts. Even measuring a qubit can collapse its delicate state too soon. This fragility is called decoherence, but rather than hearing it as a technical word, imagine it as a moment when a dancer, holding a perfect balance, suddenly stumbles because someone whispered too loudly nearby. The dancer's graceful pose vanishes in an instant. To keep coherence intact, quantum computers must shield qubits from every distraction. Wires entering the cold chamber must be filtered and cushioned to prevent noise. Lasers must be tuned so precisely that they deliver just the right amount of energy. The entire machine must sit on shock absorbers, isolated from the vibrations of footsteps, doors closing, or traffic rumbling far away. In some laboratories, even the distant hum of elevators is enough to disturb the subtle choreography of qubits. Despite this fragility, quantum computers are not helpless. They incorporate techniques to protect information even when individual qubits falter. These methods, often grouped under the idea of error correction or error mitigation, might sound complicated, but their essence is simple. Listen carefully to the qubits, notice when their whispery signals drift off tune, and gently nudge them back before the mistakes accumulate. Think of it like smoothing wrinkles from a delicate fabric or tuning a violin string that has gone slightly flat. One approach spreads information across several qubits, so that even if one or two lose their coherence, the overall pattern remains recoverable. You can imagine it as a choir where no single voice carries the melody. Instead, the melody lives in the harmony of the group. If one singer falters, the others still carry the tune, allowing the original music to be reconstructed. This strategy requires many physical qubits to create a single logical qubit, the stable building block of a future large-scale quantum computer. Another approach involves listening to the system as it runs and adjusting the signals afterward, much like enhancing a quiet recording to remove background noise. Scientists refer to this as smoothing out the noise after hearing a faint whisper. It does not eliminate every error, but it helps reveal the true quantum pattern beneath the static. Building a quantum computer is therefore less like constructing a machine and more like cultivating a delicate ecosystem. Everything must be orchestrated with extraordinary care. The qubits must be kept still, shielded, and gently guided. The environment must remain serene and cold. And the operations, those pulses, rotations, nudges, and entangling interactions, must be delivered with the precision of tapping a single grain of sand without disturbing its neighbours. All of this effort might seem excessive until you remember what qubits offer. Vast oceans of possibility, overlapping paths, and the ability to explore patterns that classical computers cannot handle. A quantum computer is like a wind harp placed in the quietest room in the world, tuned so finely that the faintest breeze creates harmonies no human hands could produce alone. To hear these harmonies clearly, we must muffle the world's noise, dim the heat, and let the universe's smallest rhythms sing. And as everything becomes colder, calmer, and more precise, something remarkable happens. The machine begins to behave less like a computer and more like a musical instrument. Each pulse of current is a note. Each laser beam is a gesture. Each entangled pattern is a chord that stretches across the qubits like a shimmering thread. In this sense, building a quantum computer is an artistic act, one that blends physics, engineering, and a deep understanding of silence. As we continue our journey, we'll step from the quiet chambers of construction to the broader question of purpose. What can these delicate machines do? What problems can they solve? And what mysteries remain out of reach? The answer, like the machines themselves, requires patience, nuance, and the gentle recognition that every tool, no matter how powerful, has its own special song. If you imagine a quantum computer as a magical engine that can solve every problem instantly, you're not alone. Many early descriptions of quantum technology carried hints of that dream. But the truth, when understood gently, is far more balanced and far more interesting. A quantum computer is not a replacement for classical computers, just as a violin does not replace a piano. Each instrument has its own voice, its own strengths, its own songs it plays better than any other. And just as an orchestra needs both strings and percussion, the future of computing will likely rely on the combined strengths of classical processors, artificial intelligence, and quantum machines working side by side. To understand what quantum computers can do, it helps to return to their strongest gift. They can explore many possibilities at once, using superposition and entanglement to guide the shape of those possibilities. This does not make them universally faster. Instead, it gives them advantages in problems that resemble complicated landscapes, places where countless paths exist, and where finding the best path is like scanning a mountain range full of hidden valleys. One of the clearest examples lies in chemistry. Molecules are governed by quantum laws. Their bonds, vibrations, and reactions arise from the behavior of tiny particles following quantum patterns. Classical computers can approximate these patterns, but the deeper you look, especially in large or complex molecules, the more memory and time are needed. A molecule with just a handful of atoms might be manageable, but as the structure grows, the number of possible electron arrangements balloons into a giant forest of possibilities that classical machines struggle to navigate. Quantum computers, however, are built from the same logic that molecules follow. A set of qubits can represent the overlapping patterns of electrons naturally. Instead of simulating quantum behavior, the computer itself behaves in a quantum way, letting chemists explore reactions with a level of detail that would otherwise be impossible. In the future, this may help design new medicines, new materials, and new catalysts that reduce energy use or capture carbon more efficiently. If classical computation is like sketching a landscape with charcoal, quantum computation is like painting it with colour. Both depict the scene, but one reveals subtle textures the other cannot. Another promising area is optimization, problems where you must choose the best option from among many. Imagine trying to schedule thousands of flights each day, or arranging delivery routes so trucks travel the shortest overall distance, or designing financial portfolios that balance risk and reward. These tasks involve navigating huge webs of possibilities, each path influencing the next. Classical computers tackle these by checking possibilities step by step or using clever shortcuts. Quantum computers, in contrast, shape the possibility landscape itself, allowing the best solutions to emerge through interference in a way that is more fluid and natural for certain structures. There is also cryptography, the art of securing information. Some of today's encryption methods rely on tasks that classical computers find extremely difficult, such as factoring large numbers. A quantum computer, using certain algorithms, could perform such tasks much more efficiently, potentially breaking some of the digital locks that protect our information. This may sound alarming, but it simply means we will adopt new encryption methods that quantum computers cannot easily break. Much like upgrading locks when new tools become available, researchers are already developing quantum-safe encryption designed to withstand attacks even from future quantum machines. Quantum computers also have a unique strength in simulating quantum systems themselves. This might seem obvious, but it has profound implications. Everything in the universe, from the carbon in your bones to the fusion reactions in stars, is a quantum system. A classical computer struggles to model these behaviors as they grow in complexity. But a quantum computer can treat them less like puzzles and more like familiar dances, using superposition and entanglement to model them directly. This could illuminate the physics of superconductors, exotic materials, or high-energy particle interactions that remain mysterious today. However, it is equally important to understand what quantum computers cannot do. They are not faster at everyday tasks like loading web pages, editing videos, or running spreadsheets. They are not replacements for your laptop. They do not excel at simple arithmetic or general tasks that classical processors handle with ease. Even solving every problem in mathematics remains far beyond their reach. Quantum machines have strengths, but also clear limitations. Another important truth is that quantum computers today are still small and fragile. Their qubits lose coherence, their operations contain noise, and their stability over long calculations remains limited. Researchers often compare today's devices to early airplanes, capable of flight, but unable to carry heavy loads or travel long distances. They demonstrate the principle, but are not yet ready for everything we envision. In the near future, the most powerful systems may be hybrids, classical computers handling the bulk of computation, artificial intelligence guiding the structure of problems, and quantum processors tackling specific parts that require exploring many states at once. You can imagine this as a trio of instruments. The classical computer keeps the steady rhythm, the AI adds complex patterns, and the quantum processor contributes shimmering chords of possibility. Together, They form a computational orchestra capable of solving problems no single tool could manage alone. For most people, the presence of quantum computers will be invisible. They will live in cloud-based labs, accessed remotely by programmers who speak to them using specialized languages. Their outputs will feed into design tools, scientific simulations, and optimization engines without ever appearing on a personal device. You may not hold a quantum computer in your hands, but the effects of their work may shape medicines you take, materials you use, and services that guide your daily life. What makes this future especially calming is that quantum computers do not threaten the familiar world of classical machines. They complement it. They offer new ways of understanding complexity, new methods for exploring possibility, and new hints about the deeper rules of nature. They're instruments built not for speed in general, but for exploration in the realms where superposition and entanglement naturally shine. As we drift into the next stage of our journey, we'll leave the hardware behind and step into something more philosophical and cosmic. We will begin to explore the idea that the universe itself may be structured like a vast network of information, that the same rules shaping qubits might also shape the stars, the galaxies, and the unseen architecture that binds everything together. If you step back far enough, far beyond the scale of atoms, beyond the sweep of planets, beyond even the swirling arms of galaxies, you might begin to sense a pattern. Not the pattern of shapes or colours, but something quieter beneath the surface, a rhythm, a structure, a kind of order that repeats itself across scales so vast they barely seem related. This is the idea that the universe, at its deepest level, might be an information structure, something woven together not just by matter and energy, but by patterns, relationships, and the quiet logic that connects one scale to another. To understand this gently, imagine tracing the shape of a fern leaf. If you break off a small piece and look closely, you'll see that the tiny section resembles the whole leaf in miniature. The pattern repeats at multiple scales. Nature loves this kind of repetition, from snowflakes to branching rivers to the filaments of galaxies. Some scientists now believe that information functions in a similar way, creating echoes across the universe. Information in this sense is not words or data files. It is the arrangement of things, how particles relate, how fields fluctuate, how forces interact. At the quantum level, information is encoded in probability clouds, entangled correlations, and the soft waves of possibility that determine how particles behave. At larger scales, information emerges as patterns, clusters of galaxies forming along dark matter filaments, stars coalescing in swirling nebulae, planets settling into orbits shaped by gravity. This idea becomes even more intriguing when we consider that quantum information, the delicate patterns that define qubits, cannot be destroyed. Even if a particle disappears, the information it carried must, in some form, remain preserved in the universe. This principle gives rise to the belief that the universe stores its own history in its structure, like faint footprints left on a trail. Every interaction, every shift, every quantum event leaves a subtle imprint, adding to a cosmic tapestry woven moment by moment. To visualize this softly, imagine a vast, calm lake. When a pebble is dropped into it, ripples spread outward, touching distant shores. Even after the ripples fade, the lake is never exactly the same as before. Something small has changed, so subtle you cannot point to it, but present all the same. In a similar way, each quantum event creates ripples in the informational structure of the universe. Those ripples may fade, but the total story they tell becomes part of the cosmic whole. Information also shapes the very architecture of the cosmos. The large-scale structure of the universe, the cosmic web, resembles a delicate lace of glowing filaments stretching across unimaginable distances. At each intersection sits a galaxy or a cluster of galaxies. The empty regions between filaments, vast dark voids, form pockets of silence. This pattern arises from the interplay between gravity, dark matter, and the tiny initial fluctuations in the early universe. Those fluctuations were themselves quantum in origin, random variations amplified into sprawling cosmic structures billions of years later. In a sense, galaxies are the echoes of quantum ripples. The cosmic web is the enlarged fingerprint of information first written when the universe was younger than a raindrop. The universe did not begin as a static object. It began as a vibrating possibility field, and the patterns of those early vibrations now fill the night sky with arcs of light. Even gravity, the force that shapes the dance of stars and galaxies, may be an expression of information. Some theories propose that gravity emerges from the way information is organized on the surface of space, much like tension in a blanket stretched tight. If you press down in one place, the fabric curves. If you tug on another, it stretches. In these theories, gravity is not a force transmitted through particles, but a reflection of how information arranges itself. You can imagine space as a quiet sheet of fabric covered in tiny grains of sand. Each grain represents a bit of information. When matter accumulates, it changes the distribution of grains, creating curves and folds in the fabric. Objects then move along these curves, following the pathways shaped by information. Whether this picture turns out to be literally true or simply a metaphor, it provides a gentle way to imagine the link between quantum rules and cosmic behavior. This perspective helps bridge the two worlds we've explored so far, quantum mechanics and cosmology. At first glance, the smallest particles and the largest galaxies could not seem more different. One dances with probability, the other drifts with ponderous slowness across billions of years. But when seen through the lens of information, their connection becomes clearer. Both are shaped by patterns built from the same fundamental rules. Even the expansion of the universe can be seen this way. As space stretches, it changes the distribution of information across the cosmic fabric. Dark energy influences how that stretching accelerates. Dark matter shapes the scaffolding on which galaxies form, and quantum fluctuations provide the seeds for structure. It is as if the universe grows by unfolding a pattern from within itself, the way a fern unfurls from the shape already encoded in its stem. This does not mean the universe is a computer, or that reality is a simulation. Rather, it suggests something gentler. The idea that the universe organizes itself through relationships. Matter and energy are not isolated objects. They are expressions of deeper informational patterns, and we, being made of the same matter and energy, are part of those patterns as well. Every breath you take, every memory you hold, every moment of awareness is supported by quantum information in your body, interacting with the gravitational structure of the world around you. You're not separate from the informational fabric of the universe. You're woven into it, a quiet, conscious ripple within the cosmic tapestry. As we drift further, we will return to the cosmic unknowns, dark matter, dark energy, and the puzzles that still whisper from the edges of our understanding. But before we step into that uncertainty, it helps to recognize that uncertainty itself is not an error. It is a doorway, and sometimes the universe reveals itself most clearly not through what we know, but through the soft outline of what remains a mystery. If there is one lesson the universe teaches us gently, again and again, it is this. What we do not know is often far larger than what we do. For all the grand discoveries of the past century, for the telescopes that peer across billions of years, the quantum experiments that probe the smallest scales, the detectors that listen to spacetime itself, we are still surrounded by mysteries. They do not confront us loudly. Instead, they wait at the edges of our understanding like quiet rooms we have not yet entered. And among these mysteries, two loom larger than the rest: dark matter and dark energy. Together they make up nearly all of the universe, yet remain almost entirely unseen. The first of these mysteries, dark matter, reveals itself through gravity, through the way galaxies spin, through how clusters hold together, through how light bends as it passes near large masses. We have spoken earlier about how Vera Rubin's observations show that galaxies rotate far faster than expected, as if each one was swimming through a hidden halo of mass. But even now, decades later, we still do not know what that mass actually is. Some theories propose that dark matter consists of particles unlike anything we have seen. They might be incredibly light, drifting through space like soft waves, or they might be heavier, interacting so rarely with ordinary matter that trillions pass through your body each second without leaving a trace. There are even ideas that the universe created tiny black holes in its earliest moments, smaller than atoms but incredibly dense, and that these miniature dark stars might still be scattered throughout the cosmos. Physicists call these possibilities a dark zoo, not in a playful sense, but to reflect the wide range of hypothetical creatures that could inhabit the universe just beyond our reach. Deep underground experiments watch for faint flashes of light that might signal dark matter colliding with atoms. Space telescopes scan for subtle distortions in the glow of distant galaxies. Particle colliders search for traces that vanish into invisible channels. Yet so far the quiet has persisted. The mystery remains. Dark energy is even more elusive. Unlike dark matter, which pulls with gravity, dark energy pushes, driving galaxies apart faster and faster. We know its effect with extraordinary precision. The expansion of the universe accelerates, but the nature of the force behind that acceleration remains unknown. It might be a property of space itself, a gentle pressure woven into the fabric of the cosmos. Or it could be something dynamic, something that changes over time, like a field rippling softly through the universe. If dark energy does evolve even slowly, it could reshape cosmic history. It might grow stronger, causing expansion to accelerate ever more dramatically. Or it might weaken, allowing gravity to reassert itself in some distant era. Our measurements of this evolution are still young, like listening to a song from far away and trying to discern whether the melody is rising or falling. The instruments are improving. New telescopes like Euclid, the Roman Space Telescope and the Vera Rubin Observatory will soon map the universe with breathtaking resolution. But for now, the nature of dark energy remains a quiet question. Then there is the Hubble tension, the mismatch between measurements of the universe's expansion from the early universe and the present day. It is a subtle disagreement, but one that refuses to go away. The early universe, observed through the faint relic glow of ancient light, suggests a slower expansion today. The nearby universe, measured through supernovae and pulsating stars, suggests a faster expansion. Both methods are built on solid ground, yet they point to different answers. This tension may be a sign that something missing lies between the two eras. Perhaps dark energy changed slightly over time. Perhaps there were interactions among particles in the early universe that we have not understood. Perhaps new physics emerged after the first few 100,000 years. The mismatch is not a crisis. It is a whisper, one that tells us our map is incomplete. Even the simplest questions about the universe remain open. What happened before the first moment we can observe? Does time have a beginning, or does it stretch into something more subtle? What lies inside a black hole, beyond the place where our equations falter? Why does the universe have the particular balance of forces that allows stars, planets, and life to exist? These questions hover like lanterns in a garden at dusk, illuminating small circles of understanding, but leaving the wider landscape quiet and dim. Quantum mechanics, for all its precision, also carries mysteries. We still do not know why measurement collapses a wave of possibilities into a single result, or whether that collapse is a fundamental feature of reality or a reflection of our interaction with it. We do not know whether entanglement connects particles through some hidden mechanism, or whether the world is simply more unified than our senses can detect. Even the vacuum, what we call empty space, buzzes with quantum fluctuations that defy easy explanation. Some theories even propose that space and time themselves arise from patterns of entanglement, that the geometry of the universe is the shadow cast by deeper informational relationships. Yet for all these unknowns, there is something deeply comforting about the openness of the universe. Mystery is not a failure of understanding. It is an invitation. Each unanswered question is a doorway into a landscape we have not yet explored. Dark matter invites us to imagine new forms of matter. Dark energy asks us to reconsider the nature of space itself. The Hubble tension encourages us to look for hidden layers of cosmic history. And the gaps in quantum theory remind us that even the smallest scales may hold secrets that no equation has yet revealed. In a bedtime sense, these mysteries add a quiet depth to the night sky. When you look up and see the Milky Way, or even a handful of stars through city lights, you are gazing into a universe that is only partially mapped. The visible stars are like the lit windows of distant houses. The true architecture of the neighborhood remains hidden in the dark, and yet the fact that we can see any of it, that we can measure, question, and wonder, means we are part of the story the universe is telling. As we move toward the final session, our journey will shift from the unknowns of today to the quiet possibilities of the future. The next decades will bring new observatories, new sensors, new quantum machines, and perhaps entirely new ideas, discoveries that will reshape what we know and gently expand the map of the cosmos once again. If you imagine the universe as a long, unfolding story, then we're reading only the first few pages. The night sky above you, the stars, the faint band of the Milky Way, the quiet shimmer of distant galaxies is just an introduction. The discoveries we have made so far feel monumental to us, and rightfully so, but compared to what lies ahead, they may one day feel like the first gentle brushstrokes on a vast canvas. As we move into the coming decades, our tools, our questions, and our ways of listening to the universe will grow more sensitive. And in that sensitivity, we may finally hear the soft details that have been hiding in the cosmic silence. To begin this final journey, imagine standing in a dark field on a clear night, and then imagine that your senses suddenly sharpen. You hear faint rhythms in the air, see tiny motions in the shadows, sense patterns you never noticed before. That is what the next generation of observatories will be for scientists. Not entirely new eyes or ears, but refined ones, capable of noticing the smallest, quietest signatures of the universe. One of these new tools is the Euclid spacecraft, designed to map the shape of the universe with extraordinary precision. Euclid looks at how galaxies stretch, cluster, and drift across billions of light years. Instead of seeing individual stars or planets, it sees patterns, like the weave of threads in a tapestry. By studying these patterns, Euclid will gently reveal how dark matter curves space, how dark energy pushes against it, and whether the balance between them has changed over time. In soft terms, Euclid is a cartographer of the cosmos, sketching not the continents and oceans of space, but the invisible currents beneath them. Alongside Euclid is the Nancy Grace Roman Space Telescope, often described as a Hubble with wide-open eyes. While Hubble focuses on narrow, deep patches of the sky, Roman will sweep across enormous portions, collecting light from millions of galaxies in a single glance. Think of it as trading a magnifying glass for a wide, panoramic window. Roman will measure how ancient starlight bends around unseen structures, helping us trace the hidden scaffolding of dark matter with a clarity never before possible. It will also search for planets, including those drifting freely through space without suns, silent wanderers invisible to ordinary methods. And then, down here on Earth, the Vera Rubin Observatory will soon begin its sweeping nighttime survey. Every few nights, Rubin will photograph the entire sky, creating a dynamic movie of the universe. Stars that brighten, fade, or flicker, asteroids shifting their paths, exploding supernovae blooming like flowers of light. This constant watchfulness will not only reveal the behaviour of galaxies and dark matter, it will uncover rare cosmic events we might otherwise miss. Rubin will be the universe's diary keeper, capturing every change. No matter how small, in a continuous flow of gentle observations. But our future explorations are not limited to the larger scales. The quantum world will also unfold in new ways. Today's quantum computers are fragile instruments, but 50 years from now they may feel as natural as electricity does today. They could become tools for modelling the earliest moments after the universe's beginning, moments where everything existed as overlapping waves of possibility. They might help design new materials that interact with light in unusual ways, or medicines shaped by the quiet patterns of electron clouds. They could even help reveal whether the information woven into black holes truly remains preserved, or whether space and time themselves arise from deeper quantum relationships. Quantum sensing will become just as transformative. Already, tiny detectors can measure acceleration, rotation, or magnetic fields with sensitivity far beyond classical instruments. Imagine networks of sensors capable of monitoring Earth's gravitational field continuously, revealing underground rivers, magma chambers, or changes in ice mass as clearly as a weather forecast. Imagine clocks so precise they can measure the rise of a mountain as tectonic forces push it upward, or detect the slight tug of nearby mass that changes the flow of time by a few trillionths of a second. These technologies will help us understand our own planet as deeply as we study the stars. And then there are the questions we haven't learned to ask yet. In the next half-century, scientists may discover entirely new cosmic ingredients, particles beyond the familiar ones, fields we have not yet imagined, or subtle interactions that bridge the gap between quantum scales and cosmic structure. Some ideas suggest that dark matter might come in multiple varieties, forming a shadow ecosystem. Others propose that dark energy might gently shift with time, like a slow tide moving through space. Future measurements may confirm these ideas or reveal something stranger and more beautiful. We might also hear new kinds of gravitational waves. Today, our detectors hear the high notes, the quick chirps from merging black holes. But future observatories, especially those placed in space, could hear deeper tones, the slow rumble of supermassive black holes colliding in distant galaxies, or perhaps faint murmurs from the universe's earliest chapters. These signals would be like listening not just to the bells of the cosmos, but to the entire orchestra. And through it all, Voyager will still be travelling. Long after the instruments on board stop speaking, long after its batteries fade, the spacecraft will continue drifting outward, an object made by human hands becoming a permanent resident of the interstellar dark. In 1 billion years it may still be there, moving silently through a place where the sun is just another faint star among many. It will carry no signal by then, no message, no hum of instruments, only the quiet truth that humanity once reached outward, long before any of us were here to see what followed. When we speak of the future, especially of such immense timescales, it can feel overwhelming. But there is peace in remembering that the universe unfolds gently. Stars live for billions of years. Galaxies drift like slow-moving clouds. Even the expansion of the universe is a calm, continuous stretching. Our next 50 years, brief in cosmic time, will be filled with discoveries, but they will arrive softly, like new brushstrokes added to a painting that has been growing for eons. Perhaps that is the real gift of science, not just the facts or the theories, but the reminder that the universe is vast, patient, and full of quiet wonders, and that we, in our smallness, can still learn to listen to it. Through telescopes, through quantum instruments, through the simple act of gazing at the night sky. As you settle into rest, you might imagine the universe not as something distant, but as something gently present. The atoms in your body were forged in stars. The breath in your lungs contains molecules older than Earth. Every moment of awareness you experience is built from quantum rhythms echoing through the same laws that guide galaxies. You're not outside the universe, observing it from afar. You're inside it, part of its fabric, a thread woven into a story that continues to unfold.